with the optical interconnect and a sort of fabric thing with FPGAs, and we demonstrated this at Interop, and it literally showed the tremendous advantages of very, very high communication bandwidth, very low power. Essentially, this is where we are headed in terms of networking architectures, right? So in summary, what we've done in the short-term work is to come up with a low-cost optical backplane, right, which with these 10 channels and all these taps and so on and so forth can send data at 120 gigabits per second. Now, instead of these optoelectronic devices or elements which can go at 10 gigabits per second, if you can push it up, and it's very easy to do this with VCSEL technology, to 25 gigabits per second, that times these 12 taps can go up to 300 gigabits per second. Now, if you use 4 colors, you can go sort of 1.2 terabits per second. That's the kind of bandwidth you are trying to get to, and you cannot get to those with copper interconnects. So that's kind of the disruption. Where we are headed with this technology is now, if you look at this, kind of really cool, but then can you think of sort of these integrating these optoelectronic devices with the electronics itself, right? The electronics will run in CMOS. So now if you have the optoelectronics in sort of the 3 PHYs and the other part, can you come up with a package? And so we came up with this system in prototype concept where we will connect up one chip, which is an optoelectronic chip, to the electronic chip through what they call through vias, and we connect the whole thing up through within the package itself. So we are essentially taking different components, the optical component, the electronic component, and putting the things together in the same package. That's in the short term. In the long term, where we are headed is large-scale integrated photonics. This is really, really exciting. So because all the stuff that we did, essentially you have the electronic part, which is all the fun stuff on your Intel and AMD and ARM-based processors doing all the funky stuff in CMOS logic, right? These NAND gates, NOR gates, and so on. And then to transmit it, you have to go on to the optical work. That's not exciting, right? So if you could put it all in the same thing, that's the grand vision, that really would be kind of interesting. So we have a series of projects in this area. In the sort of shorter term, it's looking at sort of silicon photonics, and that's kind of anyway. I'll go into each of these areas. The medium term, looking at hybrid silicon and sort of 3 PHY semiconductors and lasers and so on. Long term, looking at aperiodic gratings, sub-wavelength gratings, and the very, very long term, looking at sort of just changing fundamentally what you can do with photonics in terms of changing the compute. Instead of doing the compute with CMOS logic, let's do the compute with optics as well. So that's really, really long term. So let me kind of walk you through these things again. The reason we are doing this is we all know Moore's law, where so the performance, the sizes of the number of transistors that you can put on a chip doubles every 18 months and so on. So we know this, and we get at DesignCon, we get kind of excited. Oh, I know that next year in 18 months we'll have twice the amount of compute, right? And so you expect a lot of compute power and just put in all kinds of analytic applications on it. The trouble is your communication bandwidth is being sort of somewhat constrained through the copper interconnects. And therefore, that's kind of the motivation for photonic interconnects that I mentioned earlier. So in the sort of silicon photonics area, what we have done is, suppose you could do these photonic interconnects, not as a separate piece, but in the silicon itself, right? Then you would have a truly integrated silicon electronics and photonics. Now that's a hard problem. And so what our researchers have done is to show what kind of, so if you look at a transmission system, right, you have to have emitters, you have to have transmitters and receivers, and you have to modulate that thing. So the picture that is being shown on the right-hand side is a silicon modular, sort of a ring modulator, where there is some light that is going on the outer edge, and it's being sort of temporarily stored in that little ring which is just going around in circle. That's where I have stored the data, and you can actually modulate that thing, done all in silicon. So you can do this at 100 sort of femtojoules per bit in a bus, and if you can do this, it will cost you about 600 femtojoules in an optical crossbar. So those are the kinds of technologies that are being developed at HP Labs. In the really, really near sort of future, we are looking at technologies to do free space optics. So now, suppose you have light, right? This light is shining at me. Can I capture that light and put that on the processor running on my smartphone, right? In order to do that, you have to take this and do some funky stuff on this optical cabling and connect it up, and that's not fun, right? So can you take free space optics and connect directly to the electronics, right? That's where you're headed. So the work that is that we are very excited about, and there is a co-author sitting in the audience to make sure I am honest, right, Marco? Is to look at sub-wavelength gratings. It turns out that on silicon, if you do this grating, these are grooves that you cut, right? And people do periodic grating. So every 1 micron I'll do a grating. The concept here is if you do aperiodic grading, the first one is at 1 micron, next one is 1.2 micron, next one is at 1.15 micron. So you do aperiodic grading. Now if the gratings are at the wavelength scale, right, of optics. So this does not work. If your gratings are at hundreds of microns, you cannot do this stuff. So if your grating resolution is at the level of optical wavelength, so that's the sub-wavelength grating. Turns out if you do this aperiodic grating, you create a funnel effect. It creates like a lens. So on your piece of silicon is acting like a lens. It's collecting this light and channeling it into whatever optical stuff on the silicon holoidal waveguide or whatever you want to do. Isn't that awesome? I think it's really cool. There is more stuff that is going on at labs and around sort of taking this kind of future silicon photonic stuff and replacing the compute part. Instead of doing the compute in CMOS with some NAND gates and NOR gates, all the kind of boring stuff. Sorry, it is kind of interesting. But doing that using photonics, right? But I did not have time to go into those things. Summary is, why did I talk about this here? DesignCon is about designers doing very, very exciting designs of electronic components for end customers, right? If the end customers are seeing this problem, by year 2020, there will be 50 zettabytes of data that people will access. Some of the data coming from enterprises through structured data, some coming from these sort of 30 billion cell phones that will have all the social networks, all the tweets, all the Facebook updates and so on, and from these 1.3 trillion sensors. All that data will have to be analyzed using this super duper sort of computing architecture. And that's what you are going to design. So the designers today, you are very familiar with the electronic design methodology, right? You know how to do sort of analog design, digital design, CMOS design, etc., etc. But we think the future is optics. The future is optoelectronics, all this hybrid stuff, right? These things are being designed literally by hand. But this will only make it in the real world, right? If these things become part of the design flow of future curriculum in universities and other stuff. And that's why I wanted to talk about this to this audience. Thank you for your attention.